Hello everyone and welcome to my channel. Today we're gonna do the second lesson of point cloud processing. So let's go into it. So in this lesson, we're gonna work on the depth image and how we can get the point cloud from it. So let's go and learn that together. So as usual, we're gonna come to our Visual Studio Code and we will start working from here. And I had to create a file called main.ipymb. And I have the data file, which everything gonna be down there in the link below of my GitHub repository. So you don't have to worry about anything here. So we have the output images and we have this depth, and let's start working. So a depth image is also called a depth map, and it is an image where each pixel provides its distance value relative to the sensor's coordinates in the system. So the depth images can be captured by structured light or time of flight sensors to compute the depth data. Structured light sensors such as Microsoft Kinect. So in order for us to start doing that, let's go to the practical part. So what I done here, I import all the libraries that we need. We need the image.io version 3 as IIO, and we have NumPy as MP and matplotlib.pyplot as a PLT, and we have the Open3D as O3D. We will run this cell and everything is fine. And here we will import our depth image as I have it in the data file. So I will just call depth image, and I will just import it IIO dot imread. This is imread, and let's call the image. Let's call the image. So we will have data backslash depth image, and that is our image. So just run, everything's fine. We will move to the print details. So for me to save time, I write those and I get back to you. So here we have the image resolution. So we will print the image resolution from the depth image.shape, and we will data type from depth image.dtype, and then we will have the minimum value and the maximum value for the resolution. We're going to run that, and we will have the image resolution. We will have the data type, which is in32, and we have the minimum value, which is 0, and the maximum value is 2980. So let's take a look about our depth image. So this is our depth image where you cannot see much. If you can see here, like there is something here and we cannot see much. So in order for us to have better visualization, we will play with the contrast of the image. So we will just call the depth grayscale, and from the depth grayscale, I will just mp.array, and I will just play with the contrast of the image. You can play with these parameters the way you want. So it's not a fixed parameter. So we have the depth image over O x 0x0 FFF. That is contrast value. So D type, I will just use the D type, the value that we just have up there, and we will just equal it to numpy dot uint8. Okay, and also we will just do iio dot imwrite. We want to see the image as a imwrite. Let me first, I did that before, so I will just delete that image. So we will not have it. So we will do imwrite. We want to have it in the output. So output backslash, we will just call it grayscale. We will just grayscale, and we will just call our depth image grayscale, and we will run that. So here we go. We have the grayscale image. So now things are more able to be visualized. Here we have a table and we have a chair and we have stuff. Anyways, let's go forward. So if you are not familiar with Matplotlib as well able to do image visualization. It's all about that. So let's play with Matplotlib and display the image. So we will go and do figure AXS, and we will have the plot function, and we will just do subplots, one arrow and two columns, and we will do the AXS for the array 0 dot imshow. The imshow function is not available with the library of the image IO version 3, so it's only with the Matplotlib only. So if you go to the iio.imshow, you will not find that function. So we will come here and we will just display the depth image and depth. Yep, I pressed the wrong button. CMap, I haven't changed my keyboard if you're curious about that. We will just name it gray. And AXS, we will just set a title for that. So we will say AXS for the value 0. We will just set title. And we will just name it as depth image AXS1 dot imshow. So we will just show the depth image and we will show the grayscale image. So we will just do imshow. We have the depth grayscale, and we will just see map, and we will just call it gray as well. And does everything look good? Nope. This one should be the double quotation. Yep. And we have the AXS for 1. And we have to set a title as well. We will call it the depth grayscale or the grayscale, but we need to differentiate it from the normal grayscale. So we will just call it depth grayscale. Grayscale is one word. Grayscale image. And we will, the last thing, we want to show it. So we will just say show. We want to display. Run. Error. No error. Okay, so that's what we have here. That's what we have. We have the depth image and we have the grayscale image. Now we have important and display the depth image. So how can we estimate the point cloud from it? The first step we need to do is to calibrate the depth camera to estimate the camera metrics, and then we will use and compute the point cloud. The obtained point cloud is also called 2.5D point cloud, since it is estimated from the 2D point cloud projection depth image instead of using 3D sensors such as laser sensors. So calibrating the camera means that we have to estimate the lens and we have to estimate the sensor parameters by finding the distortion coefficients, and also we have to find the camera metrics that is adjusting and calibrating and doing the parameters. So in general, there are 3 methods to calibrate the camera. The first one is using the standard parameters provided by the factory. The second one, we have to do it manually. And playing with the parameters until we will find the exact parameters. So by calibrating the camera manually, it consists of applying one of the calibration algorithms, and such as these algorithms that it called chessboard algorithm, which is one of the very famous algorithms that you might see around. This algorithm is implemented by the ROS, or Robot Operating System, and OpenCV. The calibration of the matrix is 3x3 matrix. We will gonna call it by M, and we gonna find all the functional length of the matrix, and the optical center respectively. So for this lesson, we will use the obtained result of NYU depth dataset. And here is a picture from the NYU depth dataset. So we're gonna use that to do the calibration. All right, so let's jump into that. So the depth camera parameters, I have been set it here for you. So in order for us to save the time, so in order for you, if you want to do it yourself and you want to find that calibration, I also will gonna put for you the OpenCV this video, or this tutorial, sorry, for the OpenCV for the chessboard camera calibration. Here you will be able to deal with that, and you will find that together in the link below for my GitHub repository. So I run this link, sorry, this command, I'm talking about links. I run this command and everything is cool. Let's move to the point cloud computing. All right, so the point cloud computing means that we're gonna transfer the depth pixels from the depth image in 2D coordinate system to the depth camera in 3D coordinate system to the XYZ. So in order for us to do the 3D coordinates using the formula that I'm gonna show you now, this is the formula here. As you can see, it is this. So this is our formula that we gonna follow, and we gonna do in this formula the 3D coordinates that been computing using the following formula that you can see here, that have been taken from this paper, which is the study of Microsoft Kinect calibration. So where the depth of I and J is the depth value at row of I and column J. All right, so let's start coding the formula. So first thing first, we will create an empty string. We call it PCD. Just like me said, my things, it's a bit mess here because I am having my coffee, which is my second coffee today. So we will have the array, and then we will have the height, and we will have the width, and we will have the call it to the depth image dot shape, and we will have to have a for loop in order for us to loop it through the dimensions of the image. So we will have for the first for loop, I will have it I in the range of the height, and we will have the second for loop, it's for J in the range of the width. What did I wrote? Anyways, I will fix it. There is extra T here. So in the range of width, and we will have the Z dimension and the X dimension and the Y dimension as I show it to you in the this formula. So we will we have the Z depth I and j, and we will have the x, and we will have the y. So the x, we have the cx depth multiplied by z and divided by the f of x depth, and then we have the cy multiplied by z divided by fy depth. So we're gonna do all of that. So let's come to the z. As we can see, I'm looking at the formula. So the z gonna equal to the depth image, and that's gonna be I and j, and then we will have the x equals to j, as I can see, j minus the cx depth that we identified up here, the cx depth, and that is gonna be multiplied by z, and all of that will be divided by fx depth. And then we will have the y. The y, it's gonna be the same thing. The y gonna be I minus cy depth multiplied by z and divided by fy depth, which is exactly like this. So now you look at the equations here. So we have the z depth, I like to make them all consistent and nice. So we have the z depth of I and j, and then we have the x, which is j minus cx depth multiplied by z and divided by fx depth, and the y is I minus cy depth multiplied by z fy depth. So moving forward, so after everything runs smoothly, now we're gonna display that using the Open 3D. So we're gonna go PCD underscore O3D equals to O3D dot geometry dot point cloud, two brackets. So now we are creating a point cloud object, and then we will just call that PCD O3D dot points equals to O3D dot utility dot vector 3D vector 3D, this one, vector 3D vector for the PCD, and we have setting the PCD underscore empire as the point. So we will do the visualization now by saying O3D dot visualization dot draw geometries, two brackets, and then we will say PCD 3D O3D. So we just run that, and we should have a run here. I can see that, but nothing is there, nothing showing up. Let me check where is the mistake. All right, so my mistake was I forgot to sum everything. So I forgot to sum the equation because I have the PCD here, have been prepared for the result of this equation, but I didn't do the append. So we will just say PCD append XYZ and sum them and return the value to the PCD in order for us to have it. So I'm just gonna run that and run this, and now here we have the 3D shape look for our image, for our depth image, as you can see that, and there is a floating point out here. All right, moving forward. So now what we want to do, we want to color that depth image to the original image. So like if, let's say, let me get you the original image. So here is our original image. So what we're gonna do, we're gonna color that 3D image that we had just showed just now here, and we color it with the original colors of the original image. So what we're gonna do, we're gonna transfer the RGB coloring to the O3D or the RGB-D image. So first thing first, what we're gonna do is that we want to compute the colors of the point cloud for the from the RGB-D image, and then we will display it in the RGB in the 3D image. So first thing first, we're gonna just call the RGB image that we just saw just now. So we will have RGB image. It's equal to iio.imread read, and then we have the data backslash RGB, and that is it. So we just read the image, nothing special in this command, and we just continue, and we will display the depth and the grayscale side by side in order for us, just for the demonstration purpose. So we will just figure .axs plt dot subplots, and then we will have the 1 2, which is 1 column 2 rows. That's what 1 2 means. You have 1 row 2 columns, and we will have AXS. There is a message AXS for 0, as we did that before. So I think I will speed up that and tell you what I did. So all what I did here is the AXS show for the depth image, and then we put the CMAP as a gray, and then we set a title as a depth image, and then we show for the 1. We call it RGB. We call the RGB image, sorry, the RGB image, and then we title it and just display. So this is just a display purpose. So now we put the RGB image next to the depth image, and what we want to do is that we want to put those colors on the RGB image on the depth image. In order for us to do that, we will fall into a few steps, and the first step we gonna do, first thing first, we will transform into the RGB camera coordinate system by using this equation matrix. As you can see that we have the X, Y, Z RGBs, and we have the X, Y, Z and the R transpose. So where the R and the T are the R and T are the extrinsic parameters between the two cameras, the rotation matrix and the translation vector respectively. So let's do this. So similarly as we done in the NYU depth version 2, so I will just get you the commands because they are long to save the time. So this is the rotation matrix and this is the translation vector. Now we will, the point in the RGB camera coordinate system is computed as we can see it down below in this code. So we will convert the point from depth sensor 3D coordinate system to the RGB coordinate system. That's what we're gonna do. I know like this is sounds like a bit complicated in this tutorial, but you will get the point in a minute. So this is really important fundamentals, I believe, and you need to know it, and you need to just have the information about it. If you really feel this is a bit boring, which is I believe so, you can just skip the part and look at the total resolution. So we have the dot for the XYZ. So X, Y. I need to look at my keyboard all the time. MP dot INV for the R and dot T. So, and then we will use the intrinsic parameters for the RGB camera, and we will map it to the colors using the image coordination, and we will have to apply another. So here is our RGB camera intrinsic parameters, and then we will this will indicate the coordinates of the pixel, and we will compute it using this we convert the RGB coordinates into the RGB from the RGB camera coordinates system to the RGB coordinate system. So we will have J underscore RGB equal to, and we will have the X, we will call the X RGB, and we will multiply it by the FX RGB, and we will divide that. Am I in the right place? Yeah. We will divide that by the Z RGB. We will plus it to, actually, I'm also writing another equation. I will show it to you in a minute. CX, where is the X? CX RGB, which is here. And we will plus the width, divide by 2. And then we will do here the same thing for the I. And we just have, instead of the X, we will have the Y. And we will have the FX, we will change it to FY. And the Z remain the Z, and the CX gonna be CY, and remove the rest. Okay, so we just run that and we will get an error. That is cool. Let me check that again. So we have the JRGB int XRGB FX RGB divided by the Z RGB. I can see something. Let me fix that. All right, sometimes we have really silly errors. All what I did is I rerun this cell and this cell went fine. So now let's put all of this together and display the point cloud. So I will pause again. I'm pausing today a lot, I know, but I try to save your time and I try not to make this video long. So I had put this code together and I had run it, and I just put everything together as we have it from the back up there, and I displayed. So all what I had done is that I had been converting the pixels from the coordinate system to the depth 3D coordinate system, and then converting the point from the depth sensor 3D to the coordinate system, which is here. Then we had convert the RGB camera coordinate system, which is here, to the RGB image coordinate system, another message. And what we have here, I add a point to point cloud, which is this one, and then I add the color to the pixel if it exists, which is here, else just put zeros. And then I did the conversion of the open 3D to the point cloud, which is here. And then I did the visualization. So I will run this cell, and now we will see the 3D image colored to the original colored image. The run is taking a bit long, so later maybe we can do like some code optimization and make the code more efficient, because this is taking too long. So I am waiting. And here we go. So as you can see, that is our boxes image, as you see. There we go. And yeah, now it is colored and everything is reflected to the original image. I tried to control it, right, but I cannot. It's gonna take some time. Anyways, I just leave that. So now I will just try to make this code better and get back to you. So in this tutorial, we had learned how to compute the point cloud from the RGB depth data. And in the next tutorial, we gonna learn maybe something more interesting. If you feel like this tutorial have been a bit boring for you, so just hold it a bit and bear with me until we reach to the final tutorial, where we're gonna go and do the point cloud segmentation. And I believe that one is interesting even for me. This is not, but this one is like you need to do it. And why you need to? Because in some part of your work and in some part of your projects, you might face a similar situation and you need to come up with a solution by color the point cloud image from the RGB depth image and do this and that and make this look like that, based on the requirements that you have from a client or from your research or whatever thing you are doing. So stay tuned and see you in the next tutorial. Bye bye.